Okay, good afternoon again. In this second session, Leticia will talk about the dark matter in ATLAS and CMS.
Okay, so I will put it this way. I think it's better for seeing. Okay, so as Lucia said, I will talk about this paper. That is basically a report, in a way. It couples like many results from ATLAS and CMS in a variety of dark matter searches, and simply puts it here. So it doesn't contain a lot of details or explanations. It's just a resumed? Yeah, overview. Overview is a good way of saying this. Okay, so let me this one. Basically, it talks about some. You can see the.
Yeah, maybe you can press F11.
No, it will be worse. No, actually, it's the same thing. But okay, so it's better.
Yeah.
Okay, thank you. So this is a. I'm forgetting the word. It's um apanhado. It's a. Look at this. It's, no.
Collection, a scheme.
What, Gabi? Sorry,
A collection or a scheme.
Collection. A collection is a good word. Okay, this is a collection of types of dark matter searches at both CMS and ATLAS. So divides in some kind of considerations. In this case, this looks for heavy flavor plus dark matter. Here is invisible Higgs, decay, dark Higgs, dark photon, mono anything, and others. In this paper, they talk about the Higgs invisible decays, the dark Higgs, and the mono something. And it basically just shows the main results for these types. Okay, so first of all, in all the cases, as I said, they bring the main process, the background, the main things they did to reduce background, and then the plots. It's just this, as simple as it can be. So I'm basically resumed to the process and the plot. So in this case, they are considering monojet. So the monojet in this case comes from this bloom that is irradiated from the initial state, that the initial quarks. Then you have an additional Z boson that has an axial vector coupling that is not the Z from the standard model, and some dark matter fermions. It's a simple model, and from this they produce basically these plots that says, I mean, in all the cases, it is important. In all the cases, they are looking for a large PT missing, I mean, a large momentum in the transversal axis that is missing. So, and the majority of the cases, the plots are related to the PT missing. That's here. So, in this case, I mean, it's in all the cases because these are past results. In all the cases, we didn't detect nothing. It's spoiler. But they plot here, basically, these bands are different types of backgrounds. In this case, the backgrounds are mostly something that produces neutrinos or anything that can be reconstructed and can be conf- can be missing energy in a way that is not the dark matter. Qual é a palavra confundido em inglês?
Confused?
Confused. Yes. I forgot this. Anything that can be confused with dark matter because it can produce a missing signal. So in this case, this is a Z that produces two neutrinos and jets, and the neutrinos cannot be detected. The leptons are as well in this case not reconstructed, so they are vetoed. Most of the single leptons that are produced are vetoed. And as we can see, these black dots are the data, and these bands are the background, so it fits perfectly with the background. So basically, we doesn't have any signal. These bands, not bands, these lines right here, the red and the black one, are the models. That are basically, as I understood, buried in the background. So this plot says we are considering these models, and unfortunately, we couldn't get a signal, but we get from this other plot, we can get a exclusion region. So let me zoom in a little bit more. So in this case, we are considering that this mediator Z is a ratio depending on the dark matter mass. So it's 2 times the dark matter mass. And this band right here is, this band inside these two lines is the possible relations that we can have between the two masses that respect the correct Rayleigh abundance. So with ATLAS and CMS, we can constrain in the 95% band. We can constrain up to 2000 GeV, 2000, basically 2000 GeV for both of them. Of course, considering this fixed couplings as well. So in next case, we have mono Z that starts here. Oh, okay. So in the case of the mono Z, these are both, let me just check because the distribution of images in this paper is a bit messy. Yes, figure 6A and 6B are this one. Oh shit. Sorry. This one's. Okay, so in the case of mono Z, we have basically these two processes. And most of the cases from now on, we'll consider two Higgs doublet models. I didn't quite look further on it to know why they are only putting the two Higgs doublet model here, but it's the only model that the main model that they consider from now on.
So may I say something?
Please.
Basically, when they basically have a kind of benchmark model that they want to search. So in this case, nowadays, they are using the two Higgs double model as a benchmark model.
Okay.
And also this kind of two Higgs double model plus a scalar.
Yeah, this is exactly
this is a motivated model that people are searching for. For example, Professor Felix, that perhaps will come here. He is one of the guys who was pushing forward to the experimentalists to try to find the particles predicted by the Achilles double model. So it's from the theory The guys give like a feedback to the people in the experimental side, and then they look for something.
Okay, so it's more of a benchmark model.
Yeah, because we need to align what we are doing. And the two-week model is a very motivated. And from theory,
Yeah, I know that is a very well motivated model. I just didn't understood why it was only this one, mainly in this paper that is
It's also well
collection.
studied.
Yeah, it's well studied.
They searched a lot for the two-example model, and even within the electric precision observables. So it's kind of easier to compute stuff there and to see if it's something different from there. Because it's well studied. Well studied, I mean, well measured on ATLAS CMS. Sorry.
Yeah, like these measurements.
Yeah, well measured.
in principle, you have simplified model that is easier.
Yeah, they consider some of it.
Basically, it's an input. You know, this paper that we write saying input to the community, the experimental to LHC. So people will write these white papers and they will say, oh, I think it's better to search for this model because of this, and then they will search for this. So the community, of course, you're right, but it's not just because there are other models that could be also searched.
Okay, thank you for.
So the scalars and there are two models, right?
Oh no, in this case, yeah, it's a simplified model and a 2 Higgs doublet model plus a subscalar.
The pseudoscalar that is like an axion like particles and the dark photon there, right?
Yes.
One is vectorial.
Okay, so yeah, is a I don't know if that is a dark photon, but is a.
I think that
It's-
one is dark photon and that one is axion.
No, yeah, that this one is axion. I just don't know. I'm not sure if this is dark photon because they only say that is an axial vector mediator. They only say this. Can be
They're
dark
using
photon.
something minimal model, but it looks like
Yeah.
It can be the one component of the two-example model.
No, in this because in the case B, let me just.
simple model.
Yeah.
You don't have
Simplified
a new,
vector.
in the 2 weeks of the model, you don't have new gauge boosts. You don't have. You have just a new.
No, it's because in the 2 Higgs double model you have as well and another pseudoscalar that's AI that's AA.
It looks like
major.
two different models. It has
Yeah, it's
a-
that's what I'm trying to say.
It's a
it's
simplified
a-
model.
It's coupled with quartz.
So this A and B are two different models. One, the A is 2 Higgs double model plus pseudoscalar. That can be the axion, but pseudoscalar. And the other one is a simplified model. And this A here can be the dark photon, but it's just a axial vector mediator that is not present on the standard model. So in both cases, you have the same final states. So one part missing, one part lepton. And yeah, just to introduce the quick introduction of the 2 Higgs doublet model. In this case, we have 2 Higgs doublet instead of 1 Higgs doublet. And this way, we have a heavy Higgs, that is this H here. Another point is in this paper, sometimes they put the Higgs as lowercase h, that is the most common for the Higgs doublet model. Sometimes they put in lowercase or they just don't see it. But following the 2 Higgs doublet model, this should be the heavy Higgs. That is not the Higgs on the standard model. And you have also 2 charged Higgs and then the Higgs from the standard model, plus 1 pseudoscalar and this other pseudoscalar that is addition.
Sorry, the minor A is also
Pseudoscalar, yes.
Yes, this is
Is another one that is also added. So, in this case, they say they talk here about the main backgrounds from ZZ and WZ, and also top bar and WW processes. It's a good thing to say. They say many things, many times here is about control regions and signal regions. There is a thing that's used in collider physics. It's basically signal regions are regions that we expect to see the signal based on theoretical results or calculations. And the control regions is a way to reduce background based on data driven, because mostly background is calculated with Monte Carlo simulations that is used here. But with the control regions, we basically can produce the processes that can be background to our signal, so it can mimic our process, but and not all features. And based on what we had from the data, we can exclude some regions that we see that mostly will be background. It's basically this, just selecting some regions that will mostly be signal regions and excluding some regions to control the background. And so we have some background that also comes from data-driven results, not only from simulations. Okay, so in this case, they also show the main plot, that is this one, figure 7. For these two models, they basically show this exclusion region of the mass of the... okay. Here is the... Okay, so both of them are from the 2 Higgs doublet model. So this A here is not the axial vector. This A here is the pseudoscalar. So in this case, in both cases, they are comparing they're plotting exclusion region of the mass of the A pseudoscalar and in relation to the mass of the other A minor pseudoscalar. So these regions are the excluded ones, so everything inside here is excluded. And this line right here is to consider that this mediator here or here is really produced. It's not virtual. So we can... Sorry, Ricardo, can you remember me the term? I forgot. No, the fine.
Fine tune?
No. But it's basically this. So,
Can you repeat?
So this region is this orange region is excluded. As you can see, we have here the decay rate, the interaction rate, the decay rate, divided by the mass of both the mediator, this A, and this is excluded based on the assumption that this A is produced is not only virtual.
Okay, I'm sure.
Yeah, but we have, Ricardo knows this, we have some... Yeah, I know that I forgot the name. We have a term to talk about this. The what?
Because this is one of the...
narrow width
conditions
approximation.
for narrow width
Yes.
approximation.
Yes.
Narrow width.
Yes, narrow width approximation.
Because the width of the total width of the mediating particle divided by the mass of this mediating particle.
Yeah.
And it's to be close to 0 for the narrow width approximation to be relevant.
Yeah, so this basically excludes anything that's greater than 0.2.
Yeah, because in this case you could use the approximation of the production of the cross-section of the production of the particle times the probability of this particle produce something that you want to see, like dark matter in this case. So in the case of A, it would be, I think you are searching for this the small wave, right? So because that would be the dark matter particle in the 2x double model plus A, because there is no dark matter candidate in the 2x double model.
Yeah, but all of these models, they are being made to look for dark matter. So in this case, okay, there is no dark matter in the model, but they are considering a missing energy signal. You see?
Okay, so they are searching for the A, the mediator, but they also looking like if I find the mass of the mediator, I will have some.
They're basically constraining the plane of, like, in this model, we already excluded this region of mass. So if you want to like propose a dark matter using this model, you have to use other region of mass.
You have to also agree with the
Okay. Yes.
So do you know why they are using in the second plot the masses? They have equal masses for the heavy Higgs for the subscalar in the charged Higgs.
So, as I understood, they are not using this. This is just a line that this line represents when the mass of the heavy Higgs is equal to the mass of C plus mass of A.
Yeah, but my question is, the y-axis is for the mass.
H equal to FA equals to H plus.
Do you know why?
Y is fixed here?
Yes, why they are constraining this parallel space, yes.
Most likely to benchmark, as you said, so this should be many different cuts.
No, it's related to something which is specific for the model.
What I mean by cut is that this should be 4D plot?
No, it's not the problem. For example, what Vito told, it's related to when you try to calculate some oblique parameters of the model to relatively precision, you're gonna find that to be in agreement with some things, you need a very large degree of degeneracy. So in this case, the masses of these new scalars, besides the Higgs, should be close to each other.
Yes,
that's
why they could make a scan, but that would take a lot of work. It's just a benchmark to make it.
Yeah, it's just a case.
So this is a simplified consideration. Like,
I mean, there are close limits, of course, but it's just easier to do that, and it won't make that much difference.
Why it's the tangent of beta equal to 1?
Oh, this tangent of beta is the relation of the two vectors of the two doubletics. So the vector are equal.
These papers, usually they take one result. Sometimes they have more benchmarks. You could go to the original one and see what you're talking about, and you should benchmark there, considering.
Yeah, all of this.
Probably just one.
Yes.
All of these plots are
because of any kind of constraint. It's just a simplification.
It is because of constraint.
I don't think it's.
There are constraints, but there are probably more benchmarks.
So you're saying that this is the only possible case?
We will not talk about it because this paper is very simple, as you said. Yeah. So I'm just asking to ask him, just to discuss about it, but it's okay.
Yeah, but I don't mean it is. It's just a case. Let's consider this case.
I don't think it's just this simple, but it's also not so important to discuss about it.
No, the cases are motivated, as you said. But I think these.
I don't want to turn it now. Discussion, very big discussion. It's just a question. It's okay.
Is it just like this narrow width approximation you said? Why do they only consider for ATLAS? Is it the same one in CMS, or is there a reason to why they don't put it there?
So I actually not sure. Actually, I
Oh, so
not sure.
maybe they just forgot.
Yeah, maybe there is another plot of, because I mean all of these plots that I'm showing here are just some of the plots, or like one of the plot of a bigger paper that has many plots. So I mean I can enter in the reference from CMS, and maybe they have other plots that consider this line.
But like, so this so just to see if I got it, like I don't understand. The narrow width approximation is to consider that the mediator, or basically which one is the
Oh.
Yeah, which one is on shell there? Is it this little this little A,
This
or
one.
is it the capital A? This little
Because
A.
yes, because
This little A. So
Yeah.
if I want to just to see if I get
Uh-huh.
it.
okay.
If I want to propose a model in which dark matter will be produced by the little A, the region that I am constrained is only the part where it's shaded by orange. Is that it?
Yeah, this is excluded. The shaded
So
region
that-
is
it's only
excluded.
that region that would be excluded in my model, my hypothetical.
Yeah, that region plus the region that Atlas excluded. So the orange region is excluded by the narrow width approximation.
Yes.
The both Atlas and CMS excluded another region. So both of these
Yeah,
regions.
but like below the shaded region,
Mhm.
I can use that region if I am producing it on shell, because off shell, right?
Yes.
Okay, I'm just trying to
Yeah, this region.
understand the plot is too much
Right here.
information.
Yeah, it's much information.
The narrow with the approximation, as it said, the approximation also, so it would depend how they did the analysis. So maybe CMS is another model to do the analysis.
I'm not even entering that. I just want to like understand what is it
They might-
constraining exactly.
Then the analysis another way that doesn't meet that narrow with approximation. So we would have to check the origin.
They are very smart.
But the analyses are independent.
Yes.
Yeah, I imagine they are. I was just wondering
Wondering.
what's happening there. It's a lot of information.
Yeah.
And by the way, it's like just a small fraction that they are showing
Yeah.
in this.
Let me just check something.
Sorry,
Yeah.
sorry.
it is. No. Don't be sorry. It's good that it generates discussion. I was just checking if this A, this A is a spin one mediator. Okay.
I think that's the process they are talking about.
No. No. But yeah. It is.
Because that one above, that's
Doesn't have
No.
to.
Wait. Because
no problem.
this paper is really confusing with the images. So you have to read it to see what they are referring about. So this is a part of the mono Z, right?
Yeah.
So the processes are 6A and 6B. They are the ones that I showed you. And the plot is 7. So this is a plot 7. And the processes are these ones. So you really have to read. Yeah.
So they only consider the left one, right?
Yeah, they only consider the left one.
Why do
I don't know. But I mean, in these papers, of course, as I expect, at least, in these papers, reference papers, I think they consider both. And they have more plots. But this is like, collected information.
It's fine.
Yeah. So, going on, this is basically a presentation of some models and some constraints. It's basically this. So this process is from the mono Higgs. So in the case of the mono Higgs, as well, they are looking for large PT, missing, etc.
My question: what is the mono part? What does the mono part mean?
The mono.
It's just one Higgs be produced. Is that it? Oh, okay.
Yeah.
Okay, I don't know.
Mono.
I don't know.
I mean, I think it refers to this one. I think it refers to
We
the
have monojet,
yeah.
mono Z, mono V.
Just because it's only one.
Can
Yeah.
you show that first diagram with the image?
yeah the monojet.
So this
Right.
is monojet. Why? Because if you produce
Here.
2 parts, you would see 2 jets. Okay? But in this case, you wouldn't see anything because it's just dark matter. So you're not supposed to see anything coming out.
Yeah,
The only thing you see is something that the emission state radiated. So they're looking for something that has only one jet, the monojet search.
But in this case, a
this case,
monojet
the
would
glue.
be 2 parts.
Yeah, the gluon will generate the
The
jet.
jet is what comes out of the initial.
Initial state. Okay,
From
it's
this
like
glue.
It will be
initial
a lot of
radiation.
things. No, it will be a lot. Then in other radiation, a lot of things, and you see a jet.
Yes. So what is okay? It's a monojet. But what is a D-jet?
Dijet.
Yeah,
2
dijet.
jets.
Yes, exactly. But then you said it would hadronize. How can I know? How could I know what's coming? Why it's not 2 jets?
Because they analyze that, they make a reconstruction, they have a lot of algorithms to say this jet comes from this point. And the other part might go to another way and say this jet comes from another point. And they do that so well that, have you seen a picture of a heavy ion event?
They have kind of
It's not-
orientation, right?
No, so the heavy ion event, if you just look at it, you cannot say which jet is which because it goes all around. And they have algorithms to separate each jet. Very impressive.
But usually when you have kind of D-jets, they have different directions, right?
Yeah. So you can think about it that if they're produced, the jet is even produced back to back. So you have that one here and one there. There's an angular distribution.
For example, in the dijet scenario, you would have quarks being generated, for example, instead of this dark matter, and you're not going to study the dark matter signal. You're going to study the mediator. So the mediator that is important in this case. In this case, sorry, because
it's good. It's good.
It's your topic. Let me see just the time. Okay.
What time is it? But I mean,
Go ahead.
no, actually, this discussion is more interesting than
Let's fight. Let's see who is our next.
You know
Because
what
the
a
blue
jet
one-
is?
Yes, it's a bunch of.
I don't know.
Yeah, it's a bunch of stuff. So they're coming from this one group. It's a bunch of stuff.
But I mean, like, you can have like a gluon go into a part, and that part, and then this part goes into a gluon.
But it comes from the same place, so you see it's a cone.
It's spatial. It's a distribution in space.
But
Yeah.
it's okay, because I remember there was a talk from someone, I don't remember her name, and she said that.
wake up.
She said that there was you classify jets by their
Angular
angular
distribution.
orientation. So like, if you get another gluon here, maybe you can have like
a
a
digest.
bigger, you can have something like that. I'm just asking.
Oh, they consider
There is
here.
domain conservation.
They consider here
But
this.
like the jet is considered only for.
They have their algorithm considering all of those possibilities.
Yeah, but I'm asking if I can have it. Can I or can I not?
It's not violating energy and momentum
Yes.
conservation.
Okay, so.
But that's what they keep calculating and doing
Yeah,
crazy AI to realize that it's
fine.
Can I make a question about that? I mean, I'm kind of confused because of that, in the sense that, I mean, you have kind of your detector, right? I mean, like the pictures you see, you have kind of this. It's CMS or stuff like that, right? And here you have the place where the particles collide. Here are the detectors, and kind of this is the jet. The particle is going to collide, right? So I generate kind of a jet like this, right?
Yeah, this is a transverse
Can be
one.
a gluon, And at some point it harmonizes, so you generate a lot of stuff. Is that?
Yeah, so it's a cone.
Yeah, but in some point we will kind of align because you have just glues, can be kind of really small.
Glue doesn't have a lifetime.
Yeah, but I mean, can be just a particle. After that, then you will have the hadronizing. There will be kind of stuff like that.
Yeah, but it doesn't take any time.
The hadrons are generated instantly.
Yeah,
Okay,
Glue
instant.
doesn't have
Yes.
a lifetime.
Oh, I see.
you have the gloom, but you cannot.
You are not
Detect the gluten,
a
the glue.
glue
Yes.
passing through your detector.
Or not particle, not just.
There's no shell glue.
So we're talking about strong force.
Okay, but I mean,
Strong force, glues and quarks, you cannot see them free.
but I mean, even in all another particles, kind of Z, the W and stuff like that, you'll be kind of stuck.
they
They
don't
have
have
lifetime.
No, they have a lot of time because they have mass. The time between one, the time between one vertex and the other is related to their mass.
Yes,
Never. So if the glue has no mass,
I see. Mhm. So this is a monojet, and this is a kind of bijet. It's like that.
Yeah, but you see, even the tau, you cannot see them.
Yeah,
The lifetime is too short.
I see. Okay, great.
And inside this jet, there is a lot of hadrons.
Yeah.
And those are the hadrons that are reconstructed in the calorimeter. And then this bunch of hadrons in the same place, the algorithm could call it a jet.
Mhm.
So it's something like that. It's not one thing, it's a lot of things in the same place. A lot of hadrons in the same place. And you can categorize it as a jet.
To really understand it, we need a whole new PhD. in this
Uh,
study.
What? Which fine diagram?
the
The
two ones that you showed.
okay. This one? Yeah, the mono Z.
So this is the mono Z.
Yes.
Okay.
And the next case is mono Higgs. There's this Higgs. That also consider the two doublets Higgs model. So this is the actual Higgs from the standard model. This is not actual. I mean,
This is
vectorial. Yes, this is a pseudoscalar. Yes, and this is other pseudoscalar, which produces some visible part and some invisible part. Basically the same thing. So the background, in all the cases, they say the same. The background, the things they did to avoid background, etc. Which things are vetoed. This tangent of beta one is the same thing that we saw on the other plot. So the values are the same. And this sine of theta is related to the yes, it's the sine of theta. Let me put here. It's better to draw.
There is a reason there.
So this is the transverse. Well, x or y. This is the z. This is the theta. So the sine theta is related to the transverse plane.
It's kind of related to the mixing between both of them, right?
No, if I'm considering the sine, it's
It's not
transverse
transverse momentum.
It's not transverse momentum.
You're talking about
It's the direction. What?
Oh, so you're not talking about
Yeah, it's not momentum. It's just the angle. But I mean, this is the axis of the collider. This is the z where they collide, and this is the transverse plane. So they consider the sine of theta is just considered to the transverse plane.
It's the same theta as in spherical coordinates.
So this theta is not from the model.
It's not from the model. It's from the
from
collider
the
parameter.
geometry
Yes, from the geometry.
of the collider.
And as I said, this paper is really brief. So they just say sine of theta is this, tangent of beta is this. They don't say if they are both angles, they are both parameters, anything. But I mean, so the the main plots from ATLAS is figure 9. So they do a exclusion region as they did with the mono Z. So excluding the mass of this A pseudoscalar and this other minor A pseudoscalar. And this is a plot regarding the tangent of beta, so the relation with the two vevs. That is a new plot from the ATLAS, and this is from the CMS. Yes, it's a really beautiful plot. So they considered it's not a scan, but some different values for the mass of the pseudoscalar A, the minor A, and these bars are just the uncertainty regarding to this. So in this plot, they constrain the cross section of. I'm sorry. Let me check which cross section is this. Oh, they will not tell you here. No, below they will not say.
Can anyone help me to understand what's going on in this spot? I mean, you have the
Yes.
cross section divided by the theory cross section. So what's the meaning?
Yeah.
One is the Monte Carlo, and the other is the.
Oh, this is the multicolor cross section? I was trying to understand which cross section is this because I forgot and it's only cross section. I'm sorry. I'm so sorry.
It can be calculated by hand. It can be generated, of course, by simulation, but it can be calculated by hand.
Yeah, but you could have something like the standard model and the standard model and data. I don't know what they mean by theory. Theory is already.
I think it's the model that we are considering.
So
Yeah, but what they mean with
if it's
theory?
measured,
Can you go down, please?
No, you will not explain.
I think it's
So
measured
the-
cross section.
As I understood, this theory cross section is just theoretically calculated.
Yeah, but the other one.
The other one is what I'm trying to remember because I forgot and it's only. Yeah.
For me, it makes sense in that way.
Yeah,
But the thing
it
is,
makes.
I mean,
And this okay. So this red band is like the theory uncertainty. So
Cannot be another cross section.
yeah, it cannot be. It has so. If the theory is right, we would see the one with this uncertainty band. So yeah, I think this is the data. Yeah, so this, as I'm understanding, the parameters that are permitted for this case are these ones that the cross, this band.
So if it cross, it is
Inside that one, it's right.
Yeah, I think it's possible. If it's inside this band, as this is what I'm understanding.
but what is considered
And this
right?
is the model.
Yeah, because this is the model uncertainty. I mean, this is one, so it means that the cross section that's measured is equal to the theory, and these bands are, calculated, considered for different masses. Okay.
So inside that line is kind of when you compare the data with the theory, the model with that parameter is kind of feasible. It's kind of that.
Yeah.
Okay.
Let me see this
Every street,
exclusion. Huh?
every street is the comparison between the cross section, the data, and the theory.
Yeah.
Yeah, considering different masses for
Yeah,
MA.
different parameters.
Yes. Let me just see if they. Okay, mass. Here, I think they talk about figure 9. No, figure 10 shows. Yeah, is this 10,400 and 800? Yes, this part here. Okay, I'm sorry because my memory is really, and this paper is
It's
too
going
brief.
well because we're having to go
Always
Fun.
to
Yeah, discussions.
Discussions.
Yeah, always to discuss.
I'm having fun at least. I don't know if you are.
Yeah, I didn't expect this paper to cause such discussions, but it's good. So, oh, I lost myself.
People like it.
This, okay. So after this mono things, they consider Higgs to invisible searches. So same thing. They show first the process, which is figure 12. That is this one. Yes. Okay, so this consider vector boson fusion. So these are both vectorial bosons that fuse and produce Higgs. So this Higgs is not from the two Higgs doublet model.
It's the standard model one.
It's the standard model one, but it's capital Higgs. So
It's okay? Sorry.
it's capital Higgs because
Capital.
Yeah.
Okay.
I mean but this is the standard model one. Yeah, and
They probably took the picture from the
yeah, they took.
from
I mean,
each
this is
paper.
going to YouTube.
Yeah, you exchange. Yeah. No.
Even
It's
the
not,
time.
it's not difficult to do this image. It's even more easier to put another page there.
Yeah.
It's just to do a screenshot. But
Yeah,
Yeah, then-
using
the
the
guys
paint.
took even the type from the other diagram.
Can we exclude this video from YouTube because I mean we are
2 hours.
no, we are destroying this paper.
Oh, the paper is nice.
No, the paper is nice. It's a nice. Oh, okay, now I destroy.
I mean, this paper is awesome because the paper is nice.
Oh my God.
Time was something that will always be there. I mean,
I did not
I
have.
have my first paper where I had money going back.
Are we broadcasting on YouTube?
Yeah, it's published.
Okay.
Yeah. Are you gonna find us for that?
Yeah, because
Yeah.
I'm going to watch it.
Yeah, we're not going to find a job with those.
No.
Yeah.
Can we exclude? Okay, going on. So they look for invisible decay,
So
large
the
between.
chi-
Okay.
The chi can be. They are considered the chi as fermions or as bosons or as.
Is it like is dark matter, permanent dark matter?
Yeah, I assume it's fermionic dark matter, but they don't say.
Just something.
Yeah, dark
That's
matter. No,
fermionic.
yeah, this is dark matter, and normally chi is dark matter. Oh, it's fermionic dark matter. So I assume that all of these cases are with fermionic dark matter.
Okay.
Okay. So the plot that they generated this is, just let me check. Is figure 13, that is here. Here, okay. So
It's okay for you?
Yeah, kind of.
It's not okay for me.
Why?
wait a second.
Just color red lines.
Okay.
I'm trying
So
to.
no, this color. No, wait. These colored lines are the 68 band and 95 confidence level.
One axis.
Yeah. This is observed. This is the median, but it's just the confidence bands. These colored lines. This-
Okay, but
Yeah, this one. The cross section times the branching.
Divided by the standard.
Yeah, divided by the standard model cross section.
okay.
So this is the branching. Go down where? Sorry. Here?
Combine?
Yeah.
Did they
This is the
combine
branching
after the
fraction.
sequence?
I don't know if what you.
Divided here?
Sorry, I don't know because Victor is reading something. I don't know what.
No, I'm not reading.
Oh, sorry, because you said go down.
Did I? Sorry?
Okay.
I don't understand what is the axis.
In what image? The second one?
Both.
This one is the time that the data was took.
Yes.
Wrong one. Wrong
Yeah, it's
one.
kind of run. I mean, you took the data, you did the analysis, and from 2012 and 2016, that was the upper limit.
Okay.
This
So,
is the
and
observed.
the same in this 2016, 17, sorry, and 2018.
So they improved the.
For each one.
The analysis, and it went down.
Yeah. This is a combination of
Since they are
all of the
taking
runs.
The ratio, the standard model, it seems things are going to what it should be. I guess it's very compact.
Yeah, you're taking more data than the,
Yes. Yeah, it's increasing.
and narrow down the errors.
What do they mean with median expected?
I mean, I think it's the median of this band. I think it's the median of this band. Mediana. You take the median of this band.
But they took
This is the distribution.
Yes.
It's not,
It's not the data.
No, this is not the data.
so this is the limit that you already got from the data. So it does have
But I mean, as I understand, the median is just you're taking the median of the distribution.
But okay, but
So
the observed
it doesn't
is
depend on the
not
observed.
probabilistic analysis,
What? Sorry.
because they have two lines, right?
Mm-hmm.
The dashed and the solid
Yes.
one. The solid one is observed.
Yes.
So I suppose the observed one passed through some analysis. And
Uh,
the dashed, what is the dashed?
The dashed one is the median. So this band here is like a distribution band of I mean, this yellow, all the yellow one is 95% band, yes, expected confidence level. So this dashed line is just based on this distribution. It's just the median. So the median of the distribution, mediana. So yeah, and then you have the observed that is just not on the median, but it is still on the confidence level.
I have a question. It's not necessarily about the physics involved. It's more
Yeah.
on the statistics involved. It's
Thank you.
like, okay, so the y-axis is 95% confidence level, right? So
Yes.
And then you have like other, like
No,
what is this
y-axis
95%
is the
expected?
limit.
And what is this 68% expected?
The
What's that?
y-axis is the limit. So you measured something
Okay,
and you took out the limit from that model
at 95%.
at 95%. So it's the measured, so this is the limit, not the 95%.
So it's, I'm not,
For instance, let me.
like explain like
Please.
If you're doing statistical,
It's just that this is a
Some stuff.
complicated model.
following.
This is a complicated model. Let me give you more simple
Yeah,
limit. You want to produce a resonance, but you didn't. You just did this. And then your model said, well, it should be here. And you take a limit at, I don't know, 1 dB, and you say it cannot be heavier than 1 dB or we would have produced it.
Sure.
This is the limit. And you can make it with a statistic of 95% confidence level, whatever. But it's, the limit is this, 1 dB.
fine.
So that's what it said. This is the limit on cross section divided by the standard of cross section.
Fine, perfect.
So they calculated both of them and they said, this is the value, right?
And-
So this is the value. Now I don't know exactly.
What does this 95% and 68% expected mean? You have like 95 on the y-axis and 95. Well, I'm not,
percent inside percent.
I'm not
Yeah.
like understanding.
I think the difference is observed and expected. So this is what was observed, data, and the green and orange is expected.
So the median. I see.
The median is not dependent on
Yeah,
the
the
observed.
median
It's
is
just from
on
except.
the-
Yes, it's just theory. It is
Probably
just-
a Monte Carlo thing. No?
Yes, no.
No? Or just.
No. Yeah. It will be a Monte Carlo thing. It's just based on theory and statistical.
Oh, I see. Now I understand. I think I understand. Let me try to explain to you to see if you guys agree with me, because I'm trying to see. So in my mind, I'm seeing like you have the median, and I think they're calculating the 95 and 68% confidence level around that the median. Probably,
Yes.
Right? That's why
Yes.
the region is not on the. And then you put the 95% confidence level inside it. Since it's inside, on those regions, probably it's okay with the data. That's why they published it. Is that it?
If the observer was out of it, then there's something.
There was okay.
Yeah. Yeah, as long as the observer is inside the band.
Thank you.
I
I got it now.
Thank you,
So
Gabi.
The bars are about the urine.
So as you said, if I would have kind of a solid line outside the expected, we could say that we have something
Then
else,
there's
No.
other ways that we know.
kind of a problem in the model or something that we should observe.
Could
That,
be another model, it could be something.
It was outside.
yeah.
Yeah.
Now it's clear.
Sorry. Thank you, Gabi.
Thank you. I really enjoyed this lecture about reading experimental graphs.
Yes.
Having fun with experiments.
With graphs.
Yeah.
Power graphs.
So-
So now
oh, no.
we have to go to the right plot.
Okay. Okay. Maybe we can end with this plot because we have like more 5 more plots.
Oh.
So yeah.
It's just the page 9.
No, I mean
But it's
we are.
it's different runs. So each point is different runs.
No.
It's similar.
Yeah,
This
this
in terms
one's-
of years, the other one is-
It's kind of experiments and jets and way like that. Because you have TT
Yeah.
plus ET and jet and run 2.
Yeah. Let me just.
Different channels and different runs.
Okay, nice. It's good as well.
And they are summing for each center of mass energy, right? This is a sum for each of those.
But
Sorry, I didn't understand.
are all the data together?
Yeah. So you have like different center of masses over there.
Oh yeah,
This is the energy of the collider.
No.
Yeah.
No, the
Must
center of
be
masses.
because the runs have
Those are the
different
runs.
energies.
Those are the runs.
Yeah, the runs has different energy, so they are
It's not
combining all
summing
the
under
different
the
energies.
energies. It's just the energy of the collider.
Yeah, I mean, but which one is? Okay.
I think this is run 1. This is run 2.
They
This
are
is run 3.
combining all the data from this.
As I said.
Yeah.
And this is run 1 combination, run 2 combination, run 1
Okay,
and 2
thank you.
combination. Okay, so last case we can end in this. Okay, this is the last case. We have like more 6 plots after this, but we can ignore.
Okay,
This is the
okay,
last
the
case.
plots.
No, but it's a good discussion. It's just
I will
the
speak
time.
a bit after.
Yeah, but thank you, Gabi. You should be here on my side, actually.
You should give a lecture about reading plots.
Yeah, please give a lecture. Okay, so
Problem with that.
this last case, is the dark Higgs. So we are basically, let me show the processes. Is this one? Yes, it's this one. Okay, so we are introducing a dark, another Higgs. Yeah, another scalar Higgs, but they call it dark Higgs, the dark scalar.
Sorry, is a complete different model, or it is within the 2 Higgs model?
No, it's not within the 2 Higgs.
Okay.
It's a different model. It's just considering a dark scalar
Mhm.
that is like Higgs. So in this case, they also consider a Z prime. So let me see if this is the name of the model here.
I
just-
a U1 extension with a
Yeah.
symmetry breaking term, and then you have the dark Higgs in it.
Yeah, because they only say the dark Higgs
They don't-
model.
They don't
Yeah.
mention that, they just consider.
Yeah.
It's a random U1.
As I say here, this is the considering dark Higgs model. This is light vector model. So as I understood the difference between these ones, in this case, we consider 2 types of dark matter, the Chi1, Chi2. And we do not see a Higgs because just this one is a dark Higgs. This one is, the Z prime, as I understanding, would be the light vector. So in this case, let me see which plot is this. Okay, give 15. So here we have, okay, it's a plot excluding the mass of both the z prime and the dark Higgs. So this region right here, you can't see it. They consider some values, fixed values for the coupling. They also fix some sign of theta that is the same sign of theta that we saw earlier. So it's depending only on the geometry.
So the coupling,
sorry.
The coupling is between who?
This, let me put here, this is from the CMS. So this here, this G chi is this one, as I'm understanding.
Between Z prime and the chi.
Z prime and the chi, and the other one is from the quarks and the Z prime.
Okay.
So it's only concerning the Z prime.
Are you sure this is from the geometry?
As I understood, it is just from as I understood, because as I saw, the only thetas that we saw is this one. I mean, in this paper, it's not tell. So I was looking for, but I can check.
And the sign.
Yeah. So I would check this. Maybe it's better that if I check this.
It depends on the model.
Yeah, but these are different models.
Yeah, that's
so that's
using for all the different models.
Might be a mixing the model.
Yeah, I think it's a mixing, but another possibility is the geometry.
Yeah, because they show this in different models. It's not only in the 2 Higgs double model. It's in the 2 Higgs, in this model, and in different models. But it makes sense. It makes total sense. It's just that, just based on this paper, I was a bit lost and I was looking for what could it be. So you can be right. And I can see this right now. Maybe. Okay, no, I can't see this right now.
We can see after that.
Yeah, we can see after that.
Send the paper to us, please.
No. Oh, yeah. Okay. I can send the reference paper.
Yeah, please.
I will. Okay, but this region as well is the excluded region from. Oh, sorry. Yes. This red line represents the observed data, and as I understand, this is an exclusion region.
So
Yes.
What is
this inside here? This region inside is a region excluded from this based on these two masses. What, Victor?
What is plus minus one?
Standard deviation.
Standard deviation.
Yes.
Mm-hmm.
Yeah. So this is the band, basically the 68%.
Problem is the abbreviation.
So it's basically these plots are from the same model, but it's regarding the narrow wave approximation. So the cross sections times the duration of
Tem mais fácil eles enxergarem
Uhum.
porque é
Yeah.
Então, desses aí fica muito mais fácil enxergar aí o limite do que no modelo anterior.
Sim.
Because this y-axis is really similar to the best model. But this is concerning not the runs, but the mass of the z is better as well. So they also fix the couplings and sorry.
I'm confused again.
Okay.
This coupling is what coupling? Because we didn't see kind of G bar.
No, I think it's GL.
Oh, GL.
GL. In this case here, let me. Oh, sorry. This case here. This coupling.
Okay, so this one wasn't in the
No, yeah, the previous graph was from this model, this dark Higgs model.
okay.
And the other graph is from this model, that is the light vector model.
Yes.
So this is the coupling that we are constraining now.
I see.
This is from CMS, this is from, and this from ATLAS. So as we can see, we have a lot more plots, like a lot more plots. Oh no, not a lot more plots, just 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. We have 8 more plots. So I think it's better to, but I mean, the models that they show are just up until here. These next plots are from this summary plots that are outside the previous summary that they made. So I think we can end this plot.
So basically the paper says
we
didn't find.
No, the paper is not to get conclusions or test models. It's just a summary. Summary report is, I mean, we can see the conclusion here. ATLAS and CMS experiments has brought us more searches. Yeah, it's basically a summary of ATLAS and CMS searches considering some models. So, yeah, the summary report.
Okay. That was interesting.
Yeah, that was. Thank you, Gabi. Please put do a lecture on reading plots and collider physics.
No,
This is so experimental.
no. There are many people doing that. They will say I'm wrong.
And I will send the other paper for you guys, and I'll see better.
Are hard to understand.
It is.
So many times we are reading those plots, and we need to talk to an experimentalist to understand. It's not that trivial.
Yeah.
Masterclass of plots.
Yeah. And I'm sorry if I confused the data, because in the 2 Higgs double model, I mean, this data is considered in different models. And in the 2 Higgs double model, I didn't see any data. I just see the parameter beta. I just saw the parameter beta. And in the other model, I didn't see data as well. But it makes total sense if it's a model dependent parameter. But yeah. So I'm sorry, and keep this in mind that maybe this is a model dependent parameter. So yeah, thank you.
So let's go to the bar.
This is to... Lucia, por favor, apague essa live.
Thank you very much for attending this meeting. See you next meeting. Bye bye, guys.
Interessante, pô.
Foi a live mais. Não, foi.
Eu aprendi mais aqui do que em 2 semanas estudando.
Não, é.